advanced CNN. So convolutional neural layers are formed by filters, feature maps, and activation function. From previous lecture, we have understand that what is convolution, what is pooling, and what is the fully connected layers. So for a given image, it is natural that we can use a filter and then try to extract the some information or output. However, we can use the different size of filters, for example 1 by 1, 3 by 3, or 5 by 5. So which one we have to use for the given image? This is really a big question mark. Because of this huge variation in the location of information, choosing the right kernel size for the convolution operation become tough. A larger kernel is preferred for the information that is distributed more globally, and smaller kernel is prepared for the information that is distributed more locally. So the idea of the inception is quite simple. Why we don't try all the possible or some possible combinations, for example 5 by 5, 3 by 3, and 1 by 1, and finally we will concatenate them all together. We are using 1 by 1 convolution first, then we connect them with 5 by 5 and 3 by 3 with average pooling or max pooling. Inception modules are used in convolutional neural network to allow for more efficient computation and deeper network, though a dimension reduction with stacked 1x1 convolutions. The modules were designed to solve the problem of computational expenses as well as overfitting, among other issues. The solution in short is to take the multiple kernel filter sizes within the CNN and rather than stacking them sequentially, order them to operate on the same level. So the interesting question is why we are using 1 by 1 convolution first. As stated before, deep convolutional neural networks are computationally expensive, so to make it cheaper, the authors limit the number of inputs channel by adding an extra 1x1 convolution before the 3x3 and 5x5 convolutions. Though adding an extra operation may seem counterintuitive, 1x1 convolutions are far more cheaper than 5x5 convolution and reduced number of input channels. It is important to note, however, that the 1x1 convolution is added after the max pooling or average pooling rather than before. So the advantages of using 1x1 convolution is to make the process even less computationally expensive and to reduce the number of parameters. The more parameter in the network, so the more parameter need to be trained, which result in longer training time. As I already discussed that without 1x1 convolution, we can see that the number of operators or parameters to be trained is 120, 422, and 400. But when we use 1x1 convolution and before the 5x5 or 3x3 convolution, then the number of parameters are reduced to 12, 443, and 648. So the second idea in the advanced CNN is dilated convolution. In simple word, dilated convolution is just a convolution applied to the input with the defined gaps. With this definitions given, our input is in a 2D image. Dilation rate k equal to 1 is normal convolution, and when k equal to 2 means that skipping 1 pixel per input, and k equal to 4 means skipping 3 pixels per input. The best to see the figure below with the same k value. The motivation behind using dilated convolution are the detection of a fine detail by processing the input in high resolution and a broader view of the input to capture more contextual information, and the faster runtime with the favor parameters. So in the figure we can see the dilated convolution of 1 dilated convolution, 2 dilated convolution, and the 4 dilated convolution. The figure show dilated convolution on 2-dimensional data. The red dots are the inputs to the filter, which is 3x3, and the green area is the receptive field captured by each of these inputs. The receptive field is the implicit area captured on the initial input by each input to the next layer. The next idea in the advanced CNN is Silencery map. In computer vision, a Silencery map is an image that shows each pixel unique quality. The goal of a Silencery map is to simplify and or change the representation of an image into something that is more meaningful and easier to analyze. Silencery maps are a useful technique that data scientists can use to examine the convolutional networks. They can be used to study the activation pattern of neurons to see which particular section of an image are important for the particular feature. Let's imagine that you have an image of a dog and asked to classify it. This is a pretty simple for human to do. However, a deep learning network might not be as smart as you and might instead classify it as a cat or lion. Why does it do this? The two main reasons why the network may misclassify the image is bias in the training data or no regularization. We want to understand what made the network give a certain class as output. One way of doing this is to use the silencery map. Silencery map are a way to measure the spatial support of a particular class in a given image. So this is fairly difficult to implement by yourself, but fortunately AutoGrade can do this. The procedure works as follow. Forward pass the image through the network and then calculate the scores for every class. Enforce the derivatives of score S at last layer of all classes except class C to be 0. For C, set it to 1. Back propagate this derivative through the network and render them, and you have your silencery maps. The next topic is transposed convolution. So far the convolution we have looked at either maintain the size of input or make it smaller. We can use the same technique to make the input tensor larger. This process is called upsampling. When we do it inside of a convolution step, it is called transposed convolution or fractional striding. Transposed convolution is also known as deconvolution, which is not appropriate as deconvolution implies removing the effect of convolution, which we are not aiming to achieve. It's also known as upsampled convolution, which is intuitive to the task it is used to perform, upsampling the input feature map. So to illustrate how the transposed convolution network convolution work, we will look at some illustrated example of convolution. The first is an example of a typical convolutional layer with no padding acting on an image of size 5x5. After convolution, we end up with a 3x3 image. Now we look at the convolutional layer with padding of 1. So the original image is 5x5 and the output image after the convolution is also 5x5. Though the use of transposed convolution, we are able to increase the size of an image. So the advanced CNN, most of the advanced CNNs are too many. Here the first one is LeNet 5. LeNet 5 is a classical convolutional neural network that was introduced back to 1998 and is aimed to recognize the digits from 0 to 9. LeNet 5 is such a classical model that it consists of 2 convolutional layers followed by an average pooling layer for each and apply 3 fully connected layers in the end of the network. So the modified model is quite similar to LeNet 5 except using the max pooling layers. It has 2 convolutional and 3 fully connected layers, hence means that 5. It is very common for the name of neural network to be derived from the number of convolutional and fully network layers that they have. The average pooling layer, as we know it is now, was called a subsampling layer, and it has a trainable weight, which isn't the current practice of designing CNN nowadays. The architecture has about the 60,000 parameters. So the architecture has become the standard templates, taking convolution with the activation function and pooling layers and ending the network with 1 or more fully connected layers. As shown above, for the LeNet 5 modified model, the network takes a 32x32x3 image as an input and convolves it with the 6 5x5x3 filters and stride of 1, which result in a 28x28x6 output, and then apply to the output to the max pooling layer with the filter of 2x2 and a stride of 2, which leads to a 14x14x6 output. Then apply the same convolution and max pooling layer again to obtain a 5x5x16 output. At the end of the network, the 5x5x16 output is flattened to a vector with a size of 400x1, and then apply the two fully connected layers to it, and finally achieve the estimate output with the size of 10x1 by using the softmax function. AlexNet. The AlexNet architecture is one of the most important architecture in the deep learning, with more than 25,000 citations. This is practically unheard of in a research literature. Developed by Alex and Geoffrey Hinton at the University of Toronto in 2012. AlexNet destroyed the competition in the 2012 ImageNet large-scale visual recognition challenge, and the network was trained on ImageNet data set, a collection of 1.2 million high-resolution images having 227x227x3 pixel, consisting of 100 different classes using data automation. Using data augmentation. The depth of the model was larger than any other network at the time and was trained using GPU for 5 to 6 days. The network consists of 12 layers and utilized dropout and smart optimizer layers, and was one of the first network to implement the ReLU activation function, which is still widely used today. The network had more than 60 million parameters to optimize. In the first layer of AlexNet, the convolutional window size is 11x11x3. This is because this model is implemented to classify the input for the ImageNet, the data set, which was bigger size. Consequently, a larger convolutional window is applied in the first layer in order to capture the object. The brief structure of AlexNet can be illustrated as convolution, pooling, convolutional, pooling, convolution, then convolution, then pooling, and then 3 times fully connected layers. Notice that all the convolutional layer in AlexNet apply the same padding as the network goes deeper, more filters are used to convolve, which the height and the width of the activation functions are similar. Furthermore, dropout is used after each fully connected layer in order to address the overfitting. The total number of parameters needed to learn in AlexNet is approximately the 60 million, which are way larger than the LeNet 5. So the new in the AlexNet is they were the first to implement the ReLU as activation function. The total number of parameters needed to learn in AlexNet is approximately 60 million, which are way larger than LeNet 5. VGG16. By now, you would have already noticed that CNN were starting to get deeper and deeper. This is because the most straightforward way of improving performance of deep neural network is by increasing their size. The folks at the Visual Geometry Group VGG invented the VGG16, which has 13 convolutional and 3 fully connected layers, carrying with them the ReLU tradition from AlexNet. The networks take more layers into AlexNet and use smaller filter size, for example 2x2 and 3x3. It consists of 138 million parameters and take up about 500 MB of storage space. They also designed a deeper variant, VGG19. So the pattern of VGG16 are quite simple and uniform, that the network takes 224x224x3 image as an input, followed by a stack of 2 and 3 convolutional layers and ReLU activation function, then reduce the height and width by using the pooling layer. For the number of filters in each convolutional layer, there are 64, 128, 256 and 512. Whereas the network goes deeper, the number of filters double in each stack of convolutional layer. Overall, there are approximately 138 million parameters needed to learn. Another phenomena that the modern network also apply is that as the network goes deeper. So Inception module. This 22-layer architecture with 5 million parameter is called Inception V1. This is done by the mean of Inception module, and the design of the architecture of an Inception module is a product of research on approximating sparse structure, and each module has the main two ideas: having parallel towers of convolution with different filters, followed by the concatenation capturing different features at 1x1, 3x3 and 5x5, and then clustering them. This idea is motivated by the Aurora et al. In the paper Provable Bounds for Learning Some Deep Representation suggested a layer by layer construction in which one should analyze the correlation statistic of the last layer and cluster them into groups of units with high correlation. The correlation statistic of the last layer and clustering them into group of unit with high correlation. And the second idea is 1x1 convolution are used for the dimensional reduction to remove the computational bottleneck. The Inception module is formed by concatenating other Inception modules. It includes several softmax output units to enforce the regularization. This was a key idea which has been important in the development of the future achievements. So another interesting feature is that there is no fully connected layer at the end, and this is instead replaced with an average pooling layer. The removal of this fully connected layers result in a network with 12 times fewer parameters than AlexNet, making it much faster to train. So thank you.